base we could use to, we could represent our numbers in, because you need to have alphabetic letters to represent like 10, 11, 12, 13, so on and so forth. So we can only go up to base 37 because of the English alphabet. Now, if you decide to use upper and lowercase letters, you can go a little bit bigger. Well, so, at some point in time, we decide, well, maybe we use Klingon, kind of maybe seeing it, the Klingon alphabet had more characters in it. It actually doesn't. I think it's only 22 characters in the Klingon alphabet. And yes, there is a Klingon alphabet. It's totally a thing. Thomas, do you ever check your email? Like ever? I've sent 6 emails in the last like 3 weeks, 0 replies. Blade sent them too. All right, I need to get that thing back, and you need to check your email at least once a day. That's your homework assignment for the rest of your computer science career. What's a phone? What's one of those? Oh my gosh. Okay, so we are talking about, well, we already talked about that. And I'm sharing, everybody online can hear me. It's all up on the screen. Okay. So we are still working with creating objects, and now we want to start creating some more things, practical things with our objects. So what we're going to do is let's assume we want to model the computer science department. All right, so we're going to model the computer science department. And what does that mean? So what is this department made up of at its root level? So let's say we have rooms, right? We have rooms, and then we have doors connecting rooms, exits connecting rooms, however you want to think of it. So the computer science department is a collection of rooms where a room, well, actually, yeah, we'll put it on here. Where a room is a collection of doors. And where we're going with this is I'm going to say and inhabitants, but we're not going to quite get there quite yet, but we're going to ultimately put some things in our rooms. Because what we ultimately want to come up with, this is a little bit old school. How many of you have ever heard of something called a MUD, multi-user dungeon? So think video games, but way before we had graphics and all that stuff. So it was a text-based game, and they were our early online games run on bulletin board systems. So the idea is you go in there, you would create your character, fully text-based, and then you would be put into a world that was made up of a bunch of interconnected rooms. And a lot of times they had, it was some kind of like a medieval overlay or something like that. So you would initially come into the game at the center of town. And obvious exits would be like to the north or to the west, for example. And if you go north, then, you might see that you're, in front of a bank. And you can go west on Main Street or something like that. So you would start learning the map in your head, and get to the point where you could quickly get to, maybe the place you were going to go and hunt monsters to gain experience for your guy was in the woods northwest of town. So maybe you knew from center of town, you go north, north, west, 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 north, north. And then you're at the entrance of the forest or something like that. So you start remembering, you really had to use your imagination with these types of things, almost like reading books versus watching a movie, I guess, something like that. But in any case, what we're going to do is we're going to create a very minimal version of something like this by initially creating our map. So our map is going to be a collection of rooms. Now you can call the rooms whatever you want, but we're going to have a collection of rooms, and we're going to just cheat and use the computer science department's rooms as our room names, but you can name yours whatever you want. And then from a room, at some point, we're going to be putting a player like us into a room. So for instance, if I'm standing in this room, I might look around for obvious exits. So my obvious exit is this one door, right? So maybe, I don't know which direction we're facing right now. That's north, this is south. So we have a door to the south. Okay, so is that really north? Are you sure? Oh yeah, because that's graph node. Okay, so so we have a door to the south. So if I were to take that exit to the south, I'd end up in the whatever we call it, the CS hallway or something like that. And actually, maybe we decide to represent the CS hallway as multiple rooms because it's kind of a long type thing. So if we create a empty thing and we start deciding to create what the department looks like visually. So maybe this is our entrance there. So from there we have kind of this hallway that goes down this way. And we have a hallway that goes down this way. We kind of have a, I don't know, a room there. We have a room there. We have a little room coming off of there. We have a room coming off of there. Room coming off of there. And we have a room there. That's one nice. I might say that what S118 is there, even though it's kind of a double wide room, but we'll just represent it as one room. So we have a room in here and another room here. So that's the rough, if we say all rooms are of equal size in the department, that's the rough map of our department. But not all of these rooms have exits to all other rooms, right? So keep drawing this. Maybe we decide these are going to be our exits. All right, so when we first come into the department, we do have an exit leading from the entrance to this thing. There's an exit down this hall. As we go down the hallway, this gets us into the computer lab. This gets us into this room right here. This gets us into this room right here, but you actually can't get from the lab into this room. There's no exit there. You can get from the hallway into the room we're in right now. That gets you into S120. Still going down the hallway. There's no, well, there actually is a door here, but you can't get through it because there's stuff behind it. So we'll just say there's no door there. I've never been able to get through that door. Another exit there. Here. Here. And okay, I think that's roughly it. So that kind of shows us a visual map of the rooms in the department along with the things that connect those rooms. Make some sense? All right, so we initially want to build this guy. If we go ahead and label the rooms, what do you call this guy? S120. This is S118B. This is the lab. Let's call this guy lab 1. We'll call this guy lab 2. People used to call this the soda room. So we'll just call it that for no good reason. We had a soda machine. Well, yeah, that we had a soda thing in there that you could pay a quarter and get a soda. Now, isn't the machine still outside there, but it's not filled? We stopped. I mean, not that we don't want to fill it, just we stopped doing it with COVID and just never stopped doing it or started doing it again. Soda room. So let's call this guy Hall. Two. Hall 1. Hall 0. Well, let's make this Hall 0. Giving arbitrary names to these rooms. This is network room. This is the we'll call it the lobby. It's the room with the laser cutters. And this is the esports. Oh, esports. And then this is the entrance. Okay. So we're trying to write a computer program that models this type of thing. All right. So that's what we want to do. That's the problem we're trying to solve. So now we have to think about, okay, in terms of what I already know, how can I write a computer program that models this? And then the next step will be, how can I now use this working model? So if we just look at this picture, this little world here is made up of rooms and exits or doors, whatever you want to call them, right? And as far as we know right now, a room has a name, and then it has a collection of exits. So for instance, this room right here has actually 4 exits in it, right? This room here has 1 exit. This room here has 1 exit, so on and so forth. So a room has a name and a collection of exits. What's an exit? If that's an exit, how would you describe an exit to me? What does that guy do? It links 2 rooms. It links 2 rooms together. So an exit is a pathway that holds on to 2 rooms. It connects one room to another room. Now you could always say, well, I'm going to have one directional exits. Maybe you say an exit is a direction plus a direction plus a destination. Then you'd have to represent all these exits as 2 separate exits if you wanted to do it that way. So maybe we have from this room, we have an exit to the north that leads here. And from this room, we have an exit to the south that leads here. So you could represent it as 2 separate exits, but I think we're going to do it as just 1 exit. That'll be, I think, algorithmically more interesting. Okay. So we need to build some objects. So we're going to create a room object. We're going to say a room keeps track of a string name, and then is going to have a collection of exits. And then we need to have the ID of an exit. All right. So now if we're going to have an exit being a connection between 2 rooms, so this guy will be a room 1, a room 2, maybe a direction 1, and a direction 2, something like that. That kind of goes back to our example back here where we have a single exit or a single door, whatever you want to name it. And this guy, if you take this door towards this room, that's coming out of this room to the north, to this room. If you take this exit to this room, it's coming out of this room to the south, going to this room. So a door always links 2 rooms, but the direction that you are taking that door is dependent on the which room you're starting from. Okay, so we can figure out how we're going to solve that soon. Okay, but at first, let's just build our rooms. So in our example right now, we're actually going to say a room is just a name to start off with, because exits don't exist yet. We're not going to build them quite yet. Very soon. So let's go into our code. And we'll create a new project. Go ahead and save this guy. CSC200. Call this MUD. Multi-user dungeon is what MUD stands for. Okay. Now we're going to go ahead and create a couple of files. We'll create our room HPP here. So we're going to describe what our room looks like. So we'll have our class room. And our room will have a private section where we're going to keep track of a string name, something like that. Now, you might also say that a room has a description, but that becomes a little bit tedious to put in. You've entered a dark hallway with cobwebs in the ceiling, whatever. So that's usually how MUDs work. So we're going to keep ours fairly simple. So a room, for our perspective, is just a name. We're going to have our constructor for our room. This guy will take in a string name as a parameter. And then we probably want rooms to probably display themselves. So we'll have a void display function as well. All right. Now, in order for me to use string here, room needs to know about namespace standard. That's the guy that defines the string class. All right, so I had to tell him about that. Otherwise, it would have screamed at me about using the string type here. All right, so this is just my documentation, if you will, my header file for my room. Now we're going to go and implement room in the CPP file. And if you remember, before Thanksgiving break, we did talk about kind of the header files and the C++ files. You actually could implement all of this inside of the CPP file or inside of the header file. The names, the extensions on these files aren't all that important. What we're doing is really breaking it down into the individual pieces because that's beneficial to us right now. It's also historically accurate with how programming has historically been done. Your header file kind of shows what you're going to build. The C++ file actually builds it. And then your file that has main in it is where you actually use it. Okay. So inside of room CPP, we're going to include, I need to select C++ as my language here. That should give us some better color coding maybe. So we're going to include room HPP here. And now we want to start implementing the stuff from here. So we need to implement those two things, the constructor and the method. Now, right now, if I were just to implement these, I'm in no way actually linking this constructor to the implementation of this guy back here. In order to do that, I need to specify that, oh, I am writing this guy linked to my room class. Similarly for display, I am writing the display method linked to the room class. That's what allows these two separate files to work together. But nothing absolutely kept me from just coming in here and implementing it in here. most of you would probably say, well, that maybe seems better. But the way things should work is you should have your header files documenting what the thing is capable of, and then your implementation having all the wires in there that you don't want to look at all that often. Okay, so what will we do in here? We're going to set this particular instance of rooms name variable equal to the name that was passed in. Remember that this keyword is how an object refers to itself from within itself. We'll review that again here in a few minutes. All right, so I'm saying this particular room has a name variable, and I want to set that to whatever this guy is, name. Variables resolved to the most local definition. The most local definition of name here is this dude right here. Okay, and then for display, we'll write some stuff out. So we'll say something like cout. Maybe we'll say room this name and I'll go ahead and just sort of prepare us for where we're going with this. Obvious exits. We're not dealing with exits yet. I'll just put the word there, just kind of give us a little jump start. Here, I'll put a little tab before that. So obvious exits is kind of indented a little bit, you know, that's kind of gets us from that, you know, up to that 4K graphics type of fidelity. All right. To actually have different, well, you probably have to, you would have to have a terminal that uses ANSI, which yeah, I think we're at the mercy of whatever their output thing here is. So we're not going down that path. Okay. But historically, I mean, if you really wanted to go and it is interesting, and it is the history of really models the history of our computer programming languages. If you go down and do a search on like MUDs, multi-user dungeons, and maybe kind of search for like the history of MUDs, you'll kind of see the very, very early ones, which were completely text-based, no color, things like that. Then all of a sudden, people started having a little bit more color to differentiate like the text for the room versus like the obvious exits. So like as you were playing, your eyes could quickly find like, where can I go when I'm in this room, north, south, east, west, whatever. Maybe the other monsters that were in there, you're like a rat or something like that. And if you were in the middle of a fight, you started trying to kill the rat, there would be, you know, it would be, the fight would be going on and you would get some coloration in that. Or, you know, if you like critically hit the rat, it would have big caps, stuff to, you know, add some action to it, even though there was no graphics. It was all just done with your own imagination and that stuff. Well, then we started getting specialized clients for playing multi-user dungeons. Before that, you were just using a terminal. So then we started having MUD clients where, you know, you would still connect to it, but it would have some capabilities of showing more colors and things like that, like you were just asking. Also, some of them had built-in mapping features where it would keep track of where you'd been and start building out a map on the right. So you kind of had a visual of, you know, what the world was looking like in terms of what you had explored. Then some MUDs started making themselves compatible with certain MUD clients, so that if you happen to play that MUD using that MUD client, or they required you to play that MUD using that MUD client, you would get some extra cool features, you know, some ANSI graphics or stuff like that. You know, so you really saw them playing with all of the capabilities of like network computing before we had graphic user interfaces and the ability graphics cards that could display anything outside of 8 bits. You know, so kind of watching us hit that, human beings hit the wall with what our computing capabilities were and trying to be as innovative with that as we could. And we do the same thing today. We're just pushing it at a different level, right? So today they're trying to push 120 frames a second at 4K resolution or something like that. And, you know, so now you have to have the trade-off. How powerful are our current graphics cards? And how short, depending on the game that you're creating, how great can I make my graphics, the depth of the textures, things like that, and the action, the number, the things that are going on in order to maintain 120 frames every single second at 4K resolution. Where do I have to trade off? Do I make my gamer spend $3,000 for a graphics card? Or do I say my gamer can play this game on a $200 graphics card and we just won't make it look as good? Well, the current approach is you can have the graphics tuning stuff, right? You can turn certain things that are extra hard on the graphics card. You can turn those things off, like shadows and things like that, to hopefully gain some stuff. But we're seeing that same level of innovation today, just we're seeing it through a little bit different lens. All right, so this is what a room will be for us right now. Start off fairly simple. All right, so now we'll go back into main. Oh, first of all, since I'm using cout here, I have already included using namespace standard. So I do have access to that guy, but cout lives in IOStream. I need to make sure I give myself that library.
Could you give that library?
I could have in the other one, but I didn't use it in the other one. Yeah, so he's asking, could I have put this in here? And the answer is yes, because when I say include room HPP, it's just copying all this crap in there. All that stuff is showing up in there. But the reason I didn't put it in there is because since I'm not implementing in this file, I don't actually use this library in there. So I typically am an advocate of only include stuff where you actually need it. I did need the standard namespace in here because I use string. But I didn't need IOStream, but I do need it here because I'm using cout, which also needs the standard namespace, but I get the standard namespace by way of this dude right here. Since I'm including room HPP and room HPP uses the namespace, I have it. Well, yeah, there is. I could come in here and I can say that guy. Just a little bit funky, but it's using that same syntax as what we're doing right here. Okay, so now I've invented the very beginnings of what we've decided a room might look like. Okay, again, I want to keep making our connection back to what we're trying to accomplish. Right now, I've built this guy right here. The ability to hold effectively the concept of a room that just has a name. And I've foreshadowed the concept of exits a little bit, but we haven't built exits yet. We haven't written any code related to exits yet. Okay. So now let's go build some of these rooms. Because now I have a blueprint. I have a blueprint that I could use to build instances of these rooms. And in this case here, I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I need 14 rooms. I'm going to build 14 rooms. So I need to use that blueprint to build 14 separate instances of rooms. Make some sense? So let's go ahead and we'll just build them in this order. That way we'll forget. So we'll build the entrance first. And just as a reminder, when I build a room, the constructor takes in the name of the room, and then it sets the stuff up for me. So I'll go into main. I'll go ahead and I'll include room HPP, so I have access to the concept of rooms. I'm going to take out all this extra fluff here that I'm not using. Again, I like to only include things that I'm actually currently using. So I'll take it all out and then I'll put stuff back in as I need it. Go ahead. Yeah, because it's a comment. Yeah, it's so things that start with front slash star and end in star slash is what's called a multi-line comment. That's true in C, C++, C Sharp, Java, basically all C languages. You know, so if it ends like that, it starts like that, everything in between them is a comment. You can also make comments as a single line comment with just a slash slash. Yeah, but this is all just words. All right, so let's go ahead and let's just build one room to get the ball started. So we'll create a room pointer, and I'm going to call this guy entrance, and he's going to be a new room called entrance. And then I'll say entrance display. So I'll build an instance of my room object. So the new keyword is our real estate agent, right? He goes and finds us some memory. What kind of memory? Enough to build one of these dudes. Here's my constructor. My constructor requires me to pass it a string. That was defined right here. Here's my constructor for room. He expects a string as a parameter. The implementation of that guy says, okay, he's going to take that string and set his own field called name equal to whatever string you passed in. That's what he does. Okay. So I'll build a new room. That's going to give me a memory address. I'm going to store it in a variable called entrance, which is capable of holding a pointer, the address of a room. And then I'm going to ask that room, which I called entrance, to go ahead and display himself. So do I need to include string? Maybe I do need to include string here. Yeah. So to use the string class, it's not just the standard namespace, you also need the string library. Both of those things are needed. Pretty positive you need standard there. Yeah. All right, so here's our room called entrance. And right now I just have the words obvious exits. We're not spinning through anything there. All right, makes some sense. Okay. So now what we would do is we would probably go ahead and make all of our other rooms. So we need 14 of these guys, right? And then we want these guys to connect to each other. Now, let's just start by making 2 rooms. That way we can start thinking about our exits a little bit. Okay. So I'll go ahead and build my second room. We'll call this guy hall 1. That way we can kind of think about this exit between this guy. So this guy would have obvious exits to the north. This guy would have obvious exits to the south. Well, and some other places, but right now I'm only going to have 2 rooms in existence. Okay, so we'll create a room pointer. Hall 1 is equal to a new room. Hall 1. So I can tell hall 1 to display himself. I can tell entrance to display himself. Even though this display function was written the same, this one belongs to this particular instance of room. This one belongs to this particular instance of room. So this version of display knows about this room's name. This version of display knows about this room's name. And that information is gathered in here by this arrow name. This is how an object refers to itself from within itself. Inside of hall 1's version of display, this dot name is hall 1's name. But we don't have access to that variable called hall 1 in here. It's nowhere to be found. The scope of that variable we don't see in here. He lives out here inside of main. So that guy was born inside of main and he dies here at the end of main. He's not exposed inside of that object. So that's why inside of an object, we need this special keyword that allows us to talk about ourselves. If I'm inside of display's version or hall one's version of display, and I say this, I'm talking about my stuff. If I'm inside of entrances version of display and I say this, I'm talking about entrances stuff. All right. So display prints out the name of that particular room and then just throws the word obvious exits there because that's where we're going with this. So we tell these two guys to display themselves. We'll see that we get hall one displaying himself and entrance displaying himself. All right, questions about that? All right, so let's start thinking about exits. So an exit links two rooms. And in our current first example, we happen to have the two rooms that we're going to link, right? And then it probably has directions related to those two rooms. So if I go back to my picture here, if I'm standing in this room and I want to get my obvious exits, I want to look at the direction from this exit leading that's associated with the destination, the room that's not me. Right? When I take an exit, I want to know about the room that isn't me. So that's going to be an interesting, how do we ask that question? So let's start building an exit. We have exit header file. So we'll have our class exit. All right. So now we decided an exit's going to have a couple of different pieces of information. It's going to have a room. Well, it's going to have two rooms, the two rooms it links. So that means in order to have room stuff, we need to know about room. We're going to see here in a minute, this is actually going to become somewhat of a problem once we actually start. I'll kind of foreshadow it here. Once we actually have a collection of exits inside of our room, at that point, rooms need to know about exits and exits need to know about rooms. Because an exit, it holds on to two rooms. And a room has a whole bunch of exits. So now we actually have a circular definition where when we, so I mentioned here that whenever you have an include like this, what it effectively does is it takes the entirety of this guy and just pastes it in. So pretty soon here, I'm going to have an include exit HPP in here, right? Because rooms are going to have a collection of exits.
Yeah.
So if I'm an exit HPP, I'm going to include room HPP, which includes exit HPP, which includes room HPP, which includes exit HPP, which includes room HPP. You run out of space pretty quick. And the compiler's pretty happy to tell you that real quick, that look, I've had enough. So we're going to have to find, we're going to have to see about a workaround for that. And it's kind of similar to our idea of prototyping from before. We accomplished the same thing. So we'll worry about that in a little bit when we get to it. For right now, a room doesn't know about exits. It just will know about exits soon. All right, but we're going to just focus on exits for a moment. All right, so an exit does need to know about rooms because it does link two rooms together. So we're going to have a room pointer, maybe a room A, room pointer, room B, string direction A, string direction B, something like that. So maybe direction A is the string associated with the exit leading to room A, and direction B is the string associated with the direction leading to room B. And we'll see how it can use those guys. So now we're using strings here. So we need to include the string class using namespace standard. All right. So now we need the public section for this guy. So we're going to build an exit. And in order to build an exit, we're going to need 4 pieces of information: the 2 rooms and the 2 directions. Okay. Let's go implement this guy. So this is our header file. So now we need to build our CPP file. And we'll include exit header file. We're going to implement this guy. Let me make sure I put a semicolon in. Yeah, I did. All right. And what we're going to do here is just hook those things up. So we'll say room A is equal to room A. Room B is equal to room B. Direction A is equal to direction A. Direction B is equal to direction B. Now, let's take a minute and look at something here just to further solidify the idea of this keyword. Why did I have to say this arrow direction B here equals direction B? Why do I say this dot here, but I don't say it here? Explain what's going on with like that line, for example. Go ahead. Okay, so this guy here, all variables resolved to their most local definition. The most local definition of this guy is that guy right there. But the guy I actually want to set that value to is not. I don't want to set, if I just do it this, if I leave this off, and I say this, I'm setting this guy equal to himself. Waste of time. Okay. But let's say that you don't understand this keyword. What bad programmers would do, and you'll see this often because this keyword is something that I think a lot of programmers don't fully understand. What they'll do is they'll say, well, since all variables resolve to their most local definition, can't I just change the name of that variable? And now I can say direction B is equal to dir B. That'll work. All variables resolve to their most local definition. The most local definition of dir B is this guy right here. The most local definition of direction B, he's not found here. So he's going to bounce up to the next more global scope, which is this guy right here. So this would work. And you'll find a lot of programmers who will write that. Why is that a bad idea? Just because it works doesn't mean it's a good idea. Can you give me any sort of rationale on why that might be a bad idea? Go ahead. Well, I think what you're saying is correct. I still had the same number of variables, but it creates more unique variable names, right? So why did I name this guy dir B when originally I was pretty happy with it being called direction B? I only came up with a shorthand name for it to support this syntax, to, in many cases, make it work, right? The idea is that when we have a variable name, we should name our variables something that's meaningful for what the variable represents. I chose direction B for a reason. It seemed to make sense to name my variable direction B. Now we can, quibble over whether or not we thought direction B was a good variable name or not, but we can't make an argument that there's a great reason to call this guy something different than direction B, than the same thing I called it before, because they mean the same thing. If I was okay with calling it direction B before, and I expect my constructor to take in a value associated with direction B, there isn't a great reason not to call it the same thing. That's when I'm naming that concept of direction B. Make some sense? But that then forces us to understand this syntax where I can say the field associated with my object is called direction B. And when I'm building this object, I want you to pass me a value for direction B. And I'm solidifying that request by saying, give me the value for direction B. Okay, if I'm taking notes or something, and I want to remember your first name, I might put a little thing down that says first name. And then I ask you, what's your first name? And then you hand me your first name. I don't say first name and then say, give me F name. Just so I don't have to use the special syntax to differentiate between the first name that I've written down here and the value you give me. If I want to get something called first name, I'm probably going to ask you for first name, not give you some sort of code word. All right, that makes some sense. So it has nothing to do with this being some sort of amazing variable name. There just isn't a great reason to have this guy have a different name than whatever I decided to call it here. I picked that variable name for a good reason to begin with. I should probably stick with it. But you will see plenty of programmers in industry who will write it the other way because they don't understand the this keyword. And those are the people that went and took like boot camps and things like that. There's nothing wrong with that. You can solve up to a certain level of problem with that until you finally get into something that's a little bit too complicated, where having an understanding of the this keyword, which we're going to need today, is required. Okay, so this is what we'll have for our exit. And right now, exit's just a constructor, right? Okay. So let's go and let's build an instance of our exit now. Now, what'll be interesting here is exit actually already includes room HPP. So it's actually going to scream at us because it's going to say, hey, I already see that. So even if I do nothing else here, redefinition of classroom. All because of that header file type. Make some sense? It's screaming at me in, well, it's screaming at me inside of classroom HPP, but it's screaming at me because I had room HPP here, but I had already gotten it from exit HPP. It's in both of them. So I'm asking it to define it again. Now we do have some special directives we can give it where we can wrap this guy in, let's see, where would I put it in this case? I'll just show you the example, but we're not going to keep it this way. I have to change the order here a little bit. So I'll say, I think it's what, if and def. I think it's like that. Something along those lines. Pretty sure that's the syntax. Let's see if I can keep it different screens. I must be off of the syntax a little bit, but effectively this says, if I have not already defined room underscore HPP, this is like the special syntax for room h.hpp. It's something we're not going to use. If I haven't already defined it, go ahead and define it. So this is a conditional definition of it. And really this stuff is kind of is related to what I said earlier with the programming days back with MUDs, where we started hitting walls and had to come up with innovative ways to get around it. Okay, this is an older language. As our problems we started solving with this language got more and more complex, our need to start having separate files to you know, just in this case, we're going to have two separate objects that we're both going to use from within main. Pretty soon we'll have more than just two, but our need for having multiple files that maybe relied on each other became more and more of a thing, which that's maybe not something we considered initially. So now we get into a situation where like, okay, well, if this guy needs to know about this guy and this guy needed to know about this guy, how do I let them know about each other without getting into some sort of infinite loop by bringing the definition in? You had to find a workaround. So that's where all these, you know, like, okay, well, only redefine it if it's not defined here. So what you'd actually do is you would do the if not defined in here as well as in the other place, because you're not necessarily sure which one's going to get defined first. So whichever one it hits first, that guy's going to get through the gate. The other one, we're going to say, well, if it's already defined, just skip this. Go ahead. In this particular case, you can. So in this particular case, what he's saying is, since exit already has room HPP in it, and inside main, I'm using room, by including exit HPP, I'm gonna get room. Well, even if you did depend on that knowledge, you eventually are going to run into a situation where they depend on each other. Yeah, because we in this particular case, we were able to bail ourselves out with this just because we happen to know that we didn't have even a deeper conflict. But real quick here, we're going to have a situation where an exit needs to know about room and a room needs to know about an exit. And both of those things are independent of main. So now it's like, oh, well, if I include exit, then he gets in a loop with room. If I include room, he gets in a loop with exit. We can't solve it here. Okay. So let's go ahead and build an exit. So we'll say exit pointer. I'm going to call this guy exit 0. It's going to be a little bit harder to have naming conventions for exit. Like this is exit 0, exit 1, exit 2. I don't know what we're going to do, but far less easy to track than our room names that we've given. But such is life. So we're going to go ahead and build this exit right here, where room A, maybe we could say, is entrance with a direction heading south to entrance. Room B is hall 1 with an exit heading north to hall 1. All right, so my exit constructor wants me to give it both rooms and then the direction leading to room A and then the direction leading to room B. So my two rooms are called entrance and hall 1. And since I'm passing entrance in as room A, my exit leading to room A, I've decided was south. Since this guy was room A, this exit, if I were heading to room A, I would be going there to the south. Presumably that means I'm in the other room heading to room A. So if I'm in the other room, I would take the exit to the south to get there. Similarly, if I'm in room B, well, if I'm in room A and I'm leading to room B, I would take the exit to the north. All right. And keep in mind, this is just our approach. We just decided, okay, well, this is how I'm gonna kind of solve this problem of having a single exit that links two rooms, but having to keep track of two different directions depending on which room I'm currently in. I could have just as easily decided, you know what, let's just handle exits as one directional doors, where there's an exit leading from here to here to the north. So an exit only has a destination. It doesn't have to have a room A and a room B. It just has a destination. This exit had a destination of here to the north, whereas a secondary exit had a destination of here leading to the south. I can represent it as two separate, slightly different exits if I wanted to. There isn't necessarily a correct way of doing it. This is that human innovation type thing. We've decided how are we going to build our version of an exit where they don't all necessarily come in all shapes and in the same shape and size. That's the way we're going to solve the problem. I'm purposely picking this one because this becomes academically interesting for us when we go and say, when this guy wants to say, what are my obvious exits? And he's going to look at his collection of exits and he's going to have an exit to the north leading here. Where this guy is going to say, what are my obvious exits? And he's going to see, oh, I have an exit to the south leading here. But this exit was actually the same exit, it was the same pointer. How do they use that same pointer two different ways depending on who they are? It's going to force us to use the this keyword. All right, so that's kind of why I forced it in this direction to give us more drilling with that this keyword. All right, so now I have my single exit. We have no way of displaying an exit right now, but like we can go ahead and put that in just for the sake of argument. So let's go ahead and put in a void display. And we'll implement that. All right, and this guy, I already have namespace standard. I do. This guy's going to need IO stream for his see out stuff. All right, so when we tell an exit to display itself, why don't we go ahead and have it ask the room to display itself and then maybe do the direction. So we'll do something like this room A display. This direction A. Yeah, if I'm displaying room A, we decided that the direction to room A would be direction A. Then I'll display room B, which is to the direction B. Just proving this guy got created the right way. So if we built this the right way based on this, we should have this exit with hall 1 to the north and with entrance to the south. There's hall 1 to the north and with entrance to the south. So it's holding on to the right pieces of information for us right now. All right, questions so far? Go ahead. Mhm. You good? Okay. I don't think so, because as soon as I saw that I needed to have strings here, I would have put it up there. Oh, okay. Yeah, I mean, it's hard to keep up with it sometimes. And I know I get going pretty quick just so we can get enough stuff in. Go ahead. Not right now. I think I'm just including exit. I include exit here because exit already has room. String does not name a type. Make sure you have include string as well as namespace standard. Otherwise, I can peek at it afterwards. All right. So go ahead. Okay. Yeah, real quick, just so we can get through the rest of it, but hopefully it's something I can fix real quick. HPP, because that needs to be in double quotes. Thank you. When you use the angle brackets for it, it says, look in the default library. Double quotes say, this is one of my files. So put double quotes around room, but string should still be in the angle brackets. Okay, so now the next thing we would add in here is we're going to say, okay, well, a room now needs to have some number of exits. So we would go into room here and we would say a room doesn't just have a name. It also is going to have a collection of exits. Well, so that means that a room. So now we'll introduce our issue. All right, so we're going to include exit.hpp. And we're going to say that a room is going to have an array of exits. So that's going to be a, and this is going to freak you out a little bit, but we'll spend more time next time talking about the details. So this is going to have an exit pointer called the exits. And then maybe an int number of exits. Okay. And then in our so now I'm just keeping track of 2 additional pieces of information inside of my room. I'm keeping track of a collection of exits. Now, the reason why it's an exit pointer is, remember, arrays are collections of things, right? So if I have an int array would look like an int pointer AR. Now, if you want to, I put this in parentheses just to kind of make the connection here between these two. That's where those guys are the same. So if I am making an array is a collection of objects, but an array itself, the value an array holds is the memory address. That is the base address where the array starts in memory. And remember, arrays are stored in contiguous memory, memory in a row. All right, so every single time you ever create an array, you're going to be holding a pointer, memory address. But now you have to decide, well, what kinds of values am I holding inside of my array? In this case, the type of value I was holding is an int. In this case, I'm saying we need an array of exits. Well, what is an exit? An exit is a memory address. It's a pointer to an exit object. So that's why this is exit pointer pointer. It is an array of exit pointers. Go ahead. I'm purposely not using the square brackets here. If you remember, when we use the syntax with square brackets, that memory dies off at the end of a thing. So I'm just keeping it with memory we're going to create ourselves. So at this point, what I'm specifying is that these are consistent. This isn't some sort of special new syntax. The fact that I have 2 asterisks in a row is not actually new material. It just looks intimidating because I'm now storing something other than a primitive type like an int in my array. In this case, I was storing a flat primitive type, an int, inside of my array. In this case, I'm storing an object type inside of my array. So that's why I have an array of exit pointers. So all those exit pointers are stored in contiguous memory, but each of them points to an exit somewhere in memory. You could put the parentheses in there, I believe, if you want. I think that works. But usually it would be written this way. And this, the 2 things right next to each other isn't like a special syntax. These are separate animals. That definitely works if you just put the space in there. But usually you'd see it written like this. Another way you could write it is like that. But then you're starting to go down a line where you, how you build it, you might have scoping issues. So I would say if you just keep everything consistent in the pointer world, I have an array of exit pointers. That's what that guy is. All right. And the reason I'm keeping track also of number of exits is because you remember in C++, arrays don't know how many elements are in them. So what I'll do is when I implement this inside of room CPP, in my constructor, when a room is first born, he's not going to have any exits. We will add exits to the room. Okay, so I'm not going to change my parameters coming into my constructor, but the job of a constructor is to initialize an object. So I'm going to further build out this room inside of this constructor. All right, so I'll go ahead and maybe up top here, I do something like int max exits. Maybe I set that guy at 10, something like that. We do have something in C and C++ called macros where I can say define max exits 10, something like that. So that means anywhere in my code where I see the word max exits, it just replaces it with a 10. This allows me to kind of put in there, what's the most number of exits I want a room to have? Maybe I'm just going to say 10. Realistically, if we're going to keep our map fairly simple and just do cardinal directions of north, south, east, west, our max exits could be 4. Huh? You can. The difference here is this doesn't take up any memory. This is just a replace by the preprocessor. Yeah, but what he's asking, I mean, it's a good question. We're out of time anyway, so I'll just finish up with this and let me just put a comment in here. Build memory for array. So if I said int max exits for or const max exits. Const still requires a type. Const int max exits 4. These are equal 4. These all will, for us, accomplish the same thing. But in these two cases, we are actually defining a variable that's going to be stored in memory somewhere, where that's not something a const says we're not going to be allowed to change this. This guy says we still can change it, even though we don't intend to do it. But the reality is we're never going to reference this in our code. It's just going to be used as whenever I say this, have the preprocessor just replace it with a 4. That way, if I do change the number of max exits, I can change it in one place and it'll be experienced everywhere else. All right, so we'll come back on Thursday. We'll finish doing this, and then we'll start looking at solving the problem of having exits relying on rooms, rooms relying on exits, and how can we traverse from one room to another room through an exit when they're sharing the same exit. All right, I'll see everybody on Thursday. I'll probably do the same thing that I did for the midterm. I'll probably put the exam up by Monday morning or something like that, or Sunday night, and then it'll have to be done by probably like end of day Friday maybe. But you'll have to do it in a single sitting, but you can decide when you want to take it.